Okay, let us continue the third part of the class. Okay, before we continue the class, let us see new announcements. Okay. Oh, sorry, not this. Okay, April 21st, 2022, class videos uploaded, parts 1 and 2. Hello everyone, I have uploaded parts 1 and 2 of the class videos of April 19th. Oh, sorry, this should be 21st. Let me edit it. Okay, 21st. Okay, April 21st, 2022 to YouTube. The URLs are this and this. I will upload part 3 later. Best regards, Wei Zhen. Okay, next. The slides of chapter 2 has been updated, version 2022-0423. Hello everyone, I have uploaded the latest version of slides of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications, and machine learning. Course content slides chapter 2 slides 2022-0423.pdf. Best regards, Wei Zhen. Okay, the next new announcement is the handout of chapter 2 has been updated, version 2022-0423. Hello everyone, I have uploaded the latest version of the handout of chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning, course content, handouts, Chapter 2 handout 2022-0423.pdf. Best regards, Wei Zhen. Okay, next let us see the progress of the last part. Okay, in the last part we have taught to chapter 2 slides, page 38, handout, problem 2, solution in patience, finished. Okay, please open the handout and go to the word impatience. Okay, good. Finally, we assume impatience represented by a discount factor where 0 is smaller than beta and beta is smaller than 1. Okay, under these assumptions, an infinite horizon decision problem takes the following form. Okay, what is the meaning of infinite horizon here? Okay, it means that in the time domain, it can be the time can go to the infinity. Okay, so it is an infinite horizon decision problem. Okay, v of x0 is equal to, okay, where x0 is the state at time 0, is equal to the maximum, okay, over at. At is the action at time t, and t is equal to 0 to infinity. Okay, and summation t is equal to 0 to infinity, and beta to the power of t, and f of xtat. Okay, do you remember what is the function f? Okay, the function f is the current payoff from taking action A in state x. Okay, so f of xtat is the current payoff from taking action AT in state xt. Okay, where xt is the state at time t. Subject to the constraints. Okay, AT is in the set gamma of xt. Okay, so we can know that the possible values AT constitutes a set gamma, and gamma is a set which is related to xt. Excuse me. And xt plus 1 is equal to t of xtat. Okay, do you remember what is the function t? Okay. Please see here. We also assume that the state changes from x to a new state t of xa when action A is taken. Okay, so the state change from xt to a new state xt plus 1 when the action at is taken for all t is equal to 0, 1, 2, etc. Notice that we have defined notation v of x0. Okay, here v of x0 to denote the optimal value that can be obtained by maximizing this objective function subject to the assumed constraints. This function is the value function, so now you know why we use the letter v. Okay. It is a function of the initial state variable x0. Since the best value obtainable depends on the initial situation. So now, next we are going to explain what is the Bellman's principle of optimality. Okay, the dynamic programming. Okay, we have introduced what is the dynamic programming in chapter 1. If you forget it, please review the handout of chapter 1. Method breaks this decision problem into smaller subproblems. Bellman's principle of optimality describes how to do this. Principle of optimality. An optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Okay, see Bellman, 1957, chapter 3, point 3. Okay, please see reference 75. Okay, in reference 75, we can see that it is a book written by R. Bellman. The book title is Dynamic Programming, okay, which is published in 1957. Okay, so let us go back to the place, okay, where we cite reference 75. Okay, in computer science, a problem that can be broken apart like this is said to have optimal substructure. Okay, what is optimal substructure? Okay, you can click on it And we will go to the problem 5. What is optima substructure? Solution: in computer science, a problem is said to have optima substructure if an optima solution can be constructed from optima solutions of its subproblems. Okay, let us go back to the first optima substructure. Okay. In the context of dynamic game theory, okay, we have introduced what is game theory. Game theory in chapter 1. Okay, if you forget it, please see the handout of chapter 1. This principle is analogous to the concept of subgame perfect equilibrium. Okay, what is subgame perfect equilibrium? Okay, click on it. Okay, problem 6. What is a subgame perfect equilibrium? Okay, solution: in game theory, a subgame perfect equilibrium or subgame perfect Nash equilibrium is a refinement. Okay, what is a refinement? Okay, let us see problem 7. Okay, what is a refinement? Solution: in game theory, a solution concept is a formal rule for predicting how a game will be played. These predictions are called solutions and describe which strategies will be adopted by players and, therefore, the result of the game. The most commonly used solution concepts are equilibrium concepts. Most famously, Nash equilibrium. Okay, what is Nash equilibrium? Okay, you can click it. Okay, and it will bring us to problem 8. What is the Nash equilibrium? Okay, solution: in game theory, the Nash equilibrium, named after the mathematician John Forbes Nash Jr., is the most common way to define the solution of a non-cooperative game involving 2 or more players. Okay, then what is a non-cooperative game? Okay, let us see problem 9. What is a non-cooperative game? Okay, solution: in game theory, a non-cooperative game is a game. Okay, so it is a fundamental problem. What is a game? Okay, let us see problem 10. What is a game? Solution: a game is a strategic interaction between individuals in game theory. Okay, so let us go back to the game. Okay, with competition between individual players as opposed to cooperative games. Okay, what are cooperative games? Okay, click. Problem 11. What are cooperative games? Solution: in game theory, a cooperative game or coalitional game is a game. Okay, we have explained what is a game in problem 10. With competition between groups of players, coalitions, okay, due to the possibility of external enforcement of cooperative behavior, for example, through contract law. Okay, what is contract law? Okay, let us see problem 12. What is a contract law? Okay, solution. A contract is a legally enforceable agreement that creates, defines, and governs mutual rights and obligations among its parties. Okay, problem 13. What is enforceable? Solution. The adjective of enforce. Okay, problem 14. What is enforce? Okay, solution. To make people obey a law or to make a particular situation happen or be accepted. Okay. Okay, let us go back to enforce. Okay, then go back to enforceable. Okay, and enforceable go back to the contract law. Okay, and contract law go back to cooperative games, and cooperative games go back to here. Okay, cooperative games, and in which alliances? Okay, what are alliances? Click. Okay, let us see problem 15. What is an alliance? Solution. An agreement to work with someone else to try to achieve the same thing. Okay. Okay, let us go back to the first alliance. Okay. Alliances can only operate if self-enforcing. Okay, what is self-enforcing? Okay, let us see problem 16. What is self-enforcing? Solution. A self-enforcing agreement is an agreement that is enforced only by the parties to it. No external party can enforce or interfere with the agreement. Okay. Okay, let us go back to the first self-enforcing. Okay. Okay, self-enforcing, for example, through credible threats. Okay, what are credible threats? Okay, please click on it. And we go to problem 17. Okay, what are credible threats? Solution. A credible threat is a threat made by a player in a sequential game. Okay, then what is a sequential game? Okay, click. Problem 18. What is a sequential game? Solution. In game theory, a sequential game is a game where one player chooses their action before the others choose theirs. Please see figure 13. Okay, click. Okay, figure 13, we can see that it is a chess board. Okay, which is 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, which is an 8 by 8 board. Okay. So figure 13, chess, is an example of a sequential game. Okay, let us go back to the location we cite figure 13. Okay, so this is the sequential game. Okay, and for the sequential game, we need to go back to credible threats. And let us search for the first credible threats. Okay, here. So in credible threats, let us go back to a non-cooperative game. Okay, here, non-cooperative game, we need to go back to the Nash equilibrium. Okay, most famously Nash equilibrium. Many solution concepts for many games will result in more than one solution. This puts any one of the solutions in doubt. So a game theorist may apply a refinement to narrow down the solutions. Each successive. Okay, what is successive? Okay, let us go to problem 19. What is successive? Solution happening one after the other without any break. Okay. Let us go back to the first successive. Okay. Successive solution concept presented in the following improves on its predecessor. Okay, what is predecessor? Okay, click. Problem 20. What is predecessor? Solution: someone who had a job or a position before someone else, or something that comes before another thing in time or in a series. Okay, let us go back to the first predecessor. Okay, predecessor by eliminating implausible. Okay, what is implausible? Okay, click. Problem 21. What is implausible? Solution: difficult to believe or unlikely. Okay, let us go back to the first implausible. Okay, implausible equilibria. Okay, what is equilibria? Okay, it's the plural form of the word equilibrium in richer games. Okay, so we have explained what is a refinement. Okay, let us go back to the refinement. First refinement here. Okay, refinement of a Nash equilibrium. Okay, we have explained what is the Nash equilibrium in problem 8. Used in dynamic games. Okay, what are dynamic games? Click. Okay, problem 22. What are dynamic games? Solution: a dynamic game is a sequential game. Okay, these two are equivalent. Okay, let us go back to the first dynamic games. Okay, and the dynamic games, let us go back to subgame perfect equilibrium. Okay, let us go back to the first time it appeared. Oh, I cannot find it. Okay, so page up. Okay, here, subgame perfect equilibrium. Although that constitutes an optimal policy in this case, is conditioned on the decision maker's opponents choosing similarly optimal policies from their points of view. As suggested by the principle of optimality, we will consider the first decision separately, setting aside all future decisions. We will start afresh from time 1 with the new state x1. Okay. Collecting the future decisions in brackets on the right. Okay. What is in brackets on the right? Okay, let us go back to the previous equation. Okay, it is 25 minutes. Let us see you next time. Goodbye.